In Chapter 8.2, we were studying the factor and remainder theorems, and this was one of the problems that the book gave us. It said, given a polynomial and one of its factors, find the remaining factors. And so what we had to do is we had to take this factor here and synthetically divide the value of x to turn this into 0 into this polynomial. So just a little bit of a recap of what we did last time. We know that this is a 1, a -1, a -2, a 2, a -3, a 3, and a 0. And so our ending polynomial is going to be x squared minus 2x minus 3, which we could eventually factor into x minus 3 times x plus 1. And don't forget that the x plus 1 that was given to us can also tag along. Well, what was the point of doing this? The point of doing this is when we set all of these equal to 0 using zero product property, I can determine that x equals 3, x equals -1, and x equals -1. And in the last video, I showed you that the graph of that possibly, depending on... And what's important about that is that when we decide to graph this thing, minus any type of variations in height, I know that the graph is a cubic function and it does something kind of like this. It hits a double root here at -1 and it crosses at 3. These points here are what we call x-intercepts. And this is where the function is equal to 0. So in this chapter, what we're going to do is we're going to up it a notch, and I'm going to hold on and pause for a second. And this is the new prompt of our new problem. It says, given a function and one of its zeros, find all the remaining zeros. This is very similar to what we dealt with last time. If I gave you a function p of x, and that equaled x to the third plus 2x squared minus 3x plus 20, and instead of giving you a factor, I just simply gave you -4. What you have to identify is that the -4 is the 0, but the factor of it is x plus 4. So, keeping that in mind, we're actually going to take this number as is. We're not going to reverse the sign like we did in the last section. We're just going to take it as is and plug it into our synthetic division. So I've got 1, 2, -3, and 20. So what I'm going to do is I'm going to go ahead and synthetically divide. I get a 1, I get a -4, a -2, an 8, a -5, and a, whoops, no, should not be -5, should be +5, and I should get a -20 and a 0. Okay, what that means is that my remaining polynomial is going to be x squared minus 2x plus 5. Now, in the last chapter, we were able to factor. This time, we can't, but that doesn't bar us from being able to find all the zeros. This thing still equals 0, and I still need to find where this graph crosses the x-axis. Well, I know based on my factor it's going to cross at x equals -4. I know that. Well, how would I solve x squared minus 2x plus 5 equals 0? Well, there's a number of ways we can do this if we cannot factor this quadratic, and that is completing the square or the quadratic formula. I will choose to do completing the square this time. So I'm going to add the box to both sides. This is a -1 and a -1. So I've got x squared minus, oops, not x squared, sorry. X minus 1 quantity squared equals, this is 1 and this is -4. I'm going to take the square roots of both sides. So I get x minus 1 equals, now the square root of -4 is plus or minus 2i. I'm going to add 1 to both sides. So what I end up getting is x equals 1 plus 2i and 1 minus 2i. Or you could have just combined it into 1 plus or minus 2i. So you've got 1, 2, 3 roots, 2 of which are imaginary, 1 of which is real, and we have an exponent of 3. It makes sense for us to have that many roots. All right. So now we're going to be finding the zeros of a function, which means we may have to use the quadratic formula at some point. We may have to factor again and then set the thing equal to 0 and factor it. But it's just taking what we learned last time and adding an extra step to it. So let's go ahead and do another one. Okay, given this function g of x here, 2x to the third minus x squared plus 28x plus 51, and my 0 is negative 3 over 2. Remember, they gave you the 0, which means that you plug it in exactly as is. So what I get here are my coefficients, 2, negative 1, 28, and 51. So I'm going to drop down the 2. Negative 3 halves times 2 is negative 3. I'm going to add that down to get negative 4. Negative 3 halves times negative 4 is positive 6. I'm going to add this down to get 34. Negative 3 halves times 34 is negative 51, and that gives me 0. That's awesome. So what I get is 2x squared minus 4x plus 34 equals 0. I'm going to go and divide everything by 2 to reduce the quadratic. I get x squared minus 2x plus 17 equals 0. Right, I divided both sides by 2. And now, since I have this really simple polynomial that can't be factored, I'm going to use completing the square again. So let me rewrite this problem up here. X squared minus 2x plus 17 equals 0. Let's go and subtract 17 from both sides. So I get x squared minus 2x. Leave yourself a little bit of space, equals negative 17. I'm going to add the box to both sides. So I got negative 1 and negative 1. So I get x minus 1 squared equals, this is negative 16. So I take the square roots of both sides. I get x minus 1 equals plus or minus 4i. I add 1, and I get x equals 1 plus or minus 4i. And don't forget the last 0 was actually the first 0 that we got, negative 3 over 2. All right. Let's do one more. If I give you x to the third plus 3x squared minus 10x minus 24, and I give you negative 4, again, plug negative 4 in there, 1, 3, negative 10, negative 24. Bring the 1 down, negative 4, negative 1, 4, negative 6, positive 24, 0. So my polynomial is going to be x squared minus x minus 6. Now that can actually be factored. That is x minus, 6, x minus 3 times x plus 2. And don't forget that x plus 4 was the factor that came from here. So that means that my zeros are going to be at x equals 3, negative 2, and negative 4. Okay, let's move on to something a little more difficult. When they want to make the problems harder, what they'll do is they'll give you a polynomial and they'll give you an imaginary root. And when you do an imaginary root, it's not much harder, but you have to consider that you have to create a polynomial that can be divided into the original function so that you can figure out where the other zeros are. In order to create a polynomial using an imaginary number, you have to, or rather a complex number, you have to also understand that its conjugate is also going to be part of the equation. So, kind of like, and let me just back this up for a second. Remember when we had something like, say, x to the third minus 5x squared plus 4x plus 3. And you don't have to write this down or anything, but remember when one of the zeros was negative 4, you would go x plus 4. Or let's say you had the same equation or the same polynomial and the 0 that they gave to you was 5. So that became x minus 5. This is the same thing here. This is really x minus 4 minus I. This thing here is really x minus 4 plus I. And so what you're going to do now is you're going to FOIL this expression so that you can get a polynomial that can divide into the original function. So let's go ahead and FOIL this out. Now, do not distribute your negatives or anything like that. Just FOIL it out normally and everything will work out fine. X times x is x squared. X times this thing is negative x parentheses 4 plus I. Again, we've got negative x parentheses 4 minus I. And now we've got positive, because negative times negative is positive, 4 minus I times 4 plus I. Looks kind of nasty, but don't worry, it'll clean up really well. I'm going to distribute now, so I get negative 4x plus xi. I've got negative 4x plus xi. And now with the conjugate, remember I only have to multiply the first and the last, so I got 16 minus I squared. And don't forget the x squared on the outside here. So this is negative 1, so that's, negative 1. So 16 minus negative 1 is positive 1, so this is 17. The xi's should always cancel each other out. They should always cancel each other out. And so I end up with negative 8x here, and then x squared. Now, what that's given me is that's given me the polynomial that I can use to divide into here. Problem is that it's x squared, which means that I can't use synthetic division. I have to use long division in order to find the rest of my zeros. So let's go ahead and do it. Okay, x squared goes into x to the third x times. I'm going to multiply all of this stuff in. I get x to the third minus 8x squared plus 17x. My signs are all going to reverse, so that goes away. I end up with 3x squared minus 24x, and then I'm going to bring down the 51. X goes into 3x, x squared goes into 3x squared 3 times. I'm going to end up with 3x squared minus 24x plus 51, and if I subtract the entire thing, you'll find that the entire thing goes away. I end up with x plus 3. So what that means is that x plus 3 was one of my factors. X minus 4 minus I was one of my factors. And x minus 4 plus I was one of my other factors, which means that my zeros are going to be x equals 3, and then 4 minus I, and 4 plus I. Those are your 3 zeros for this polynomial. Okay, I think we need to do one more of those just so that you guys can get the hang of it. Okay, number 5 here, x to the third minus 7x squared plus 16x minus 10. The root that they give to you is 3 minus I, which means that 3 plus I must also be a root. So I'm going to go ahead and write this out as a binomial that can be multiplied. So it's x minus the quantity 3 minus I times x minus the quantity 3 plus I. Now I'm going to go ahead and FOIL this out. This is x squared minus x times 3 plus I minus x times 3 minus I plus 3 minus I times 3 plus I. Now remember, this whole time I'm just trying to create a polynomial that can be divided back into the original function. And I'm doing that because I'm trying to find the rest of the zeros of the function. So let's go and distribute this in. This is negative 3x minus xi. This is negative 3x plus xi. And this is 9 minus I squared here, and an x squared here. So let's go ahead and clean everything up. The xi's should go away. All imaginary numbers should go away when you create your new polynomial. So you should end up with x squared minus 6x. This is negative 1, so minus negative 1 plus 10. And this is going to be what divides into this. So let's do it. x squared minus 6x plus 10 divided into x to the third. Okay, so what I get is x squared goes into x to the third x times. I distribute that in. I get x to the third minus 6x squared plus 10x. Let's go ahead and subtract and switch all of my signs. Gone, negative x squared plus 6x minus 10. X squared goes into negative x squared, negative 1 times. I'm going to redistribute. I should get negative x squared plus 6x minus 10. What do you know? When I subtract that whole thing, everything goes away. So my final factor is x minus 1, and then it's going to be x minus 3 minus I, and then x minus 3 plus I. Now this step here you don't need to take care of really. I'm just showing you what it looks like. This will give me x equals 1. This will give me the 3 minus I, and this will give me 3 plus I. And there are your three roots right there. Moving on, we are going to actually move backwards, and it's writing the equation of a polynomial with the given roots. So let's go and reset our numbers back to 1 here. If I gave you a polynomial with the roots 5, negative 2, and 7, what you have to understand is how to write these in terms of a binomial that involves x. So this would be x minus 5, this is x minus 2, and this is x minus 7. Whoops, x plus 2. And what we do is we just FOIL this out and figure out what we've got. We've got x squared plus 2x minus 5x minus 10. Let's combine our like terms here. That's x squared minus 3x minus 10. And then we're going to multiply the x minus 7 into that. So I got x to the third minus 3x squared minus 10x minus 7x squared plus 21x plus 70. And now I'm going to go and combine my like terms. I get x to the third minus 10x squared. Those are gone. Plus 11x plus 70. And that is my polynomial function. So again, you just write these with the opposite symbols involving an x, FOIL it out. Only way they can make this harder would be to give you an imaginary root, but that's easier, believe it or not. If I gave you the roots 2 and say 4i, remember you need something that will cancel the 4i out, so you need its conjugate, which is negative 4i. So now we just rewrite this as x minus 2, x minus 4i, and then x minus negative 4i or x plus 4i. Now, FOIL smart. Do not FOIL not smart. FOIL the conjugate first because the inners and outers cancel each other out. I get x squared negative 16 times I squared is positive 16. And this is being multiplied by x minus 2. I get x to the third plus 16x minus 2x squared minus 32. So rewriting that into standard form is x to the third minus 2x squared plus 16x minus 32. Okay, the following roots, negative 2, 1 plus I. This is easy. This is x plus 2. Don't forget about your conjugate. This is 1 minus I. So what I need is x minus 1 plus I. And then x minus 1 minus I. So let's go ahead and FOIL this out. This is x squared minus x times 1 minus I minus x times 1 plus I, and then plus my conjugates, 1 minus I times 1 plus I. Let's go ahead and distribute in. I get negative x plus xi, negative x minus xi from this side. X squared comes along, and I get 1 minus I squared. So 1 minus I squared. I squared is negative 1, so 1 plus 1 is 2. Those are out of there. X squared minus 2x plus 2 being multiplied by x plus 2. Again, x to the third minus 2x squared plus 2x plus 2x squared. Ooh, this is kind of a neat problem. Minus 4x plus 4. Those are gone. X squared, x to the third minus 2x plus 4 looks like my polynomial. Okay? That just about does it. We'll see you next time.